All right. Well, first, anybody have any questions about what we've been talking about? You might not remember what we were talking about because there was the test in there. Um, but we've been talking, we're now talking about two-dimensional particle kinetics, um, where we're including forces in things. And we talked about free body diagrams. And so for a free body diagram, um, you draw an outline of the object. I guess I'll. So first, just an outline of the chosen object. It's a way to be very clear to yourself about what's the boundary of the thing that you're talking about. Um, and once you draw that outline, you indicate all the forces that are acting on the chosen body. So you're going to do that first by drawing an arrow down that represents the weight, the force applied by gravity. And then second, you're going to indicate all the contact forces, all the places where the chosen body is making contact with the outside world at its boundary. So contact forces. And those contact forces fall into two categories, the way you treat them. One is if you don't know the direction of that force, I don't tolerate tardiness in this class anymore. If you don't know the force direction, then you indicate it with, you draw the little coordinate system and you use the, that's okay. I only tolerate tardiness for alternate people, so the next person's really going to get it. If you don't know the force direction, you draw the small coordinate system and you use the subscript notation. The other possibility is that you do know the force direction. And if you do know the force direction, you draw an arrow in that known direction and label it just with a scalar variable, R, F, or whatever. All right, so I'm saying all this sort of to remind you where we are with this stuff. We've talked about free body diagrams, how to indicate the weight force, the contact forces if you don't know the direction. We know all that. And now we're starting to go through the handful of force types of contact forces where we do know the direction. The first one we talked about that falls into that category is cable forces. Okay, so let's say what, okay, how about when do we know the force direction? So the first example that we saw was forces applied by cables. The second type that we're going to see is contact along a flat surface. And I guess really, instead of just contact, this should be frictionless contact because we'll see we have to deal with it a little bit differently if there's friction. But those are the two things. Those are the two cases. I think that's right. Those are the two cases where we're going to know the direction of the force. We've done this one, or we're sort of in the process of talking about that. And today we're going to get to this second one too. Yep, question? Yeah, except since I guess the only case where the only place that would come up is in the free body diagram, like at the last little part of the problem set. And I'm not expecting too much on that because we haven't, we won't have really talked about that much. You can just indicate that with a force vector. I just want you to only draw the outline and be clear to yourself that there are two forces acting, the weight force and the contact force with the incline. And other than that, that's, sort of anything's fine. Any other questions right now? All right. And for the cable force, we did the example where the mass was hanging from a cable that was connected to a hook in the ceiling. And we talked first about the force that the cable applies to the mass. And then we figured out, based on that, what's the force that the cable applies to the ceiling hook, right? And so now we're going to do an example that has a pulley in it. So let's say that there's a pulley here. This is all just walls and ground and stuff. And there's a cable attached to a mass. Let's say this mass is 10 kilograms. And the other end of the cable attaches to the wall. And let's say that what we want to know is what's the force vector applied to the wall by the cable. So the way we're going to go about it, it really is just the same exact method as the problem with the hook and the mass hanging from it. The only difference is in this case, the pulley changes the direction of that force. So what we're going to do is isolate this mass, figure out the tension in the cable, and then since the tension in the cable stays the same all along the cable, even when it goes over pulleys, then we can use that tension to figure out the force vector applied to the wall. So first I'll do a free body diagram of the mass. What forces are acting on the mass? There's one other one too. Gravity, yep. So first, there's a force acting down 10 kilograms times 9.81 meters per second squared, so 98.1 newtons. And then the second piece, now we're just sort of mentally going around the boundary of the mass, looking for places where the outside world makes contact with the boundary. And the only place is at that cable. So I mentioned last time you can make a little stump of include just a little tiny bit of that cable in the free body diagram. And then the force comes directly out of that stump. I'll call that T. And so based on this free body diagram, Newton's second law says so we're going to add up all the forces in the free body diagram. We have one force of 98.1 acting down. And then we have another force of T acting up. So what would that be in components? 0t. Yep. You can think of it, you know, there's a few ways you can think of it. You can think of it as it's acting completely along the positive y, completely in the positive y direction with a magnitude of t. So you can just think that's going to be 0 positive t. Or you can think of it as, you know, imagine putting a small coordinate system at the tail of that vector and looking for the angle from the positive x-axis. In this case, the counterclockwise angle. In this case, that would be 90 degrees. So you'd have t times cosine of 90, t times sine of 90. Cosine of 90 is 0, sine of 90 is 1, so you get 0t that way too. Okay. So the force vector is 0t. And then those two added together are equal to the mass, 10 kilograms, times the acceleration. What's the acceleration of that mass? Just hanging there, so it's 0. And so we get two equations. The x equation says 0 equals 0. So that doesn't do us any good. The second equation says negative 98.1 plus t is equal to 0. So t is equal to 98.1. So now that we've figured out the tension in the cable, we know the magnitude of the force that the cable's applying to the wall. We just have to figure out the direction so that we can express it as a force vector. Okay. So to think about that, let's draw a free body diagram of a piece of the wall. Wall chunk. Everybody wall chunk tonight. Okay, so if this is a little piece of the wall, and why didn't I take the whole wall? Like, why did I take a piece of the wall? Well, it has to do with the closed boundary thing. Like you have to be able to draw an enclosed outline of whatever you're isolating. So if I took the whole wall into account, we'd still have to deal with the fact that the wall's connected to the floor and the ceiling, you know. Somewhere we have to deal with the fact that it's connected to something else. So I just chose the little piece of the wall that the cable's attached to. So what forces are applied to the wall chunk? The first one is gravity. And we don't know how much gravity there is, but there's some. Because we don't know the mass of that piece. And then where is the outside world touching this chunk? The cable, yep. So that force is going this way. And now we know what the magnitude of that force is because we calculated that. And is the outside world touching this anywhere else? One more place. The wall. So you can call that like the force on the chunk by the rest of the wall. And we don't know what that is. So we have too many variables to solve for anything here. But the lucky thing is the only thing that we care about is we're just trying to express this force in components. Okay. And that we can do. So if we know that the magnitude of that force is 98.1, and we know that it's acting in this direction, what are the components going to be? Well, again, you can think of it two ways. First, it's 98.1 newtons acting in the positive x direction. So just from that, you know it's going to be 98.10. The other thing you can do is imagine putting the tail of this vector at the origin of the coordinate system. And then, so if the origin's here, how far, like what angle do you have to go counterclockwise from the positive x-axis to get to this vector? 360 or 0, either one. And so 98.1 times cosine of 0 is 98.1. 98.1 times sine of 0 is 0. And so you get that the force vector applied, let me erase this just so you don't get confused, because I'm going to use that C for the cable here. We're looking for the force on the wall by the cable. And that is 98.1 newtons, 0. Any questions about that? Okay. Well, the next question is, if all a pulley does is change the direction of the force, like you've probably heard of pulley advantage and the fact that pulleys are considered one of the small number of simple machines that decrease the amount of force that you have to do to, complete some task. So if a pulley only changes the direction of a force, what's pulley advantage? So just going back over basically the thing we just did, if you had something that, let's say that the weight of this car is 10,000 newtons. So it's about, around 1,000 kilograms. mg then is 10,000 newtons. And say that you were lifting this car by putting a cable over a pulley, and then here's you. You're all, oh, this car's so heavy. You go. But you're super weak. Look how skinny your neck is. Little sweat things coming out. That's how you know you're working hard. Wearing a full body jumpsuit. Okay, so what would be the force that this person would have to apply, the magnitude of the force that this person would have to apply to hold up this 10,000 newtons? 10,000 newtons, because, you could isolate the car, you'd calculate that the force and the tension in the cable was 10,000 newtons, and then, so that has to be the force the cable's applying to the hands too, okay? So there's no advantage here. The person still has to apply 10,000 newtons of force to hold up the car. So now think about the same, you're trying to do the same thing. You're still trying to hold up this 10,000 Newton car. But instead of a single pulley, say that the car is connected to a pulley that's just hanging in space, supported by a cable attached to the ceiling here, and another pulley that's attached to the ceiling like that. This pulley is attached to the ceiling, and the other one is just hanging on the cable attached to the car. You see what I mean? And I don't know, the picture's sort of inconclusive. Like, it looks like he's still working hard, but there's no sweat things. So we're going to have to do the math to figure out what the force is. Okay, so let's take a free body diagram of the car and the hanging pulley, that whole system. So there's the car. And there's the cable going up to the hanging pulley, and there's the hanging pulley. What forces are acting on this system? Gravity. So there's 10,000 newtons acting down, plus whatever the weight of the pulley is, but we're assuming that's negligible. And now go around the boundary and figure out where there's contact between this isolated body and the outside world. What? Yeah, so, and actually we're just, so you can think of it as, here's what I'm isolating. And now all you're trying to do is figure out where something crosses that boundary, where something contacts that boundary. And the place is the two pieces of cable, right? So I am going to do what I did before, include two little stumps of cable where the cable touches the body. So we have that and that. Okay. And it's just a single cable that crosses that boundary in the two spots. So we know that the tension has to be the same in both places. So we have a T there and a T there. And so Newton's second law says 0, negative 10,000. That's the force vector applied by gravity, plus 0t, plus 0t, right? I'm just going through the free body diagram and entering the force vectors for each force that's in the free body diagram. So Newton's second law says 0, negative 10,000, plus 0t, plus 0t is equal to the mass times the acceleration. We'll assume, again, that it's not accelerating. We're just trying to figure out the force to hold it in place. So that is the mass times the acceleration of 0, 0. And so the first equation gives us 0 equals 0. The second equation gives us negative 10,000 newtons plus 2t is equal to 0. And that tells us that t is equal to 5,000 newtons. Half as much. And, you know, I went through that sort of quickly. It probably hard to totally feel convinced when you go through something that quickly. But probably your first reaction to that would be, you know, there was some little trick in there. Something I did doesn't work. And so we got this result that doesn't make any sense. But the truth is, this is correct. And with pulleys that we have in lab, we could pretty easily set up a system like this and see that the force required to hold, the car or whatever up with this system with a hanging pulley supported by a pulley attached to the ceiling, you really do have to apply half as much force. It's like a really weird fact, but it's true. Yep. No, it depends on the way it's rigged up. Like if you had it like this, let's see. This doesn't have the same effect. So it's very dependent on the way it's set up. Yep, question? Because we looked for the places where outside objects contact the chosen body at its boundary, and there were two places. One here and one here. Under here? Well, this is a different cable. I mean, this is not connected to the cable that he's pulling on. But you would just see that would end up just sort of boring. That would tell you that this is applying a 10,000 Newton force up.
Is there a way to reduce it more with more pulleys?
Yes, there is. Yep, that's exactly right. So this doesn't do it. You need a specific configuration. So it's not just the fact that there's two pulleys. It's the way they're set up. So let me draw a picture that would give you a bigger reduction. So there's the ceiling. And let's say the big mass is hanging from this system of 4 hanging pulleys. And the cable that's being pulled on attaches to the ceiling. These are all attached to the ceiling. And now the cable threads through like this, to that one, to that one, to that one, to that one. Okay. And the question is, what's the tension that has to be applied to this cable to hold those up? Yep. Yeah, that's exactly right. Yep. So in order to, yeah, so like in this example, holding it up, you made holding it up a lot easier. You had to make a little trade-off though if you actually want to lift it, say a meter up into the air, 10 meters up in the air, because now in order to pull the car up 10 meters, you have to pull this out 20 meters. And you have that effect even more strongly as you add more pulleys. So I'm not going to go through the whole calculation, but just to see how this works. Okay, so we're isolating this much. There's a weight acting down of 10,000 newtons. And now contact occurs at 2 spots for each of these hanging pulleys. Each one of these forces has a magnitude of T. And so this 10,000 Newton force acting down ends up being counteracted by 8 upward forces by the cable. And so you get 10,000 divided by 8 in that case. Yep. Yeah, we're always going to assume that. Yep. And they use setups like this in shipping and places where big masses have to be moved around a lot. They'll rig up systems like this. These are called a block and tackle. I don't know what that refers to, but if you ever hear that phrase, that's talking about a system that takes advantage of this pulley advantage. Yep. Okay. So for your free body diagram, you always have the choice of choosing as your free body anything that you can draw an imaginary line through. Like anything that can be wrapped in 3 dimensions, it's like anything that you could imagine wrapping in shrink wrap, But at some point you have to define that boundary, That boundary can go way out this way, but at some point you have to close that boundary. Okay, and so, where was it? So the shrink wrap that I chose went around the hanging pulley, the car, and just a little bit of cable. Okay, imagine snipping off the cable just an inch above where it contacts that hanging pulley. Okay, and all of that stuff is your isolated body. Can you picture that? Okay. And then now that's the free body.
In this example here, is there a reason for not including the second?
Well, if you did that, you would have to calculate what the force is. So yeah, let's think of some other alternatives. I think that's a good, I think a lot of times, like when I do these example problems, I just jump right to what's the thing to isolate that lets you solve the problem. And I think sometimes it is helpful to see some free body diagrams of the stuff that doesn't let you solve the problem. So what if we did So let's say, I'm going to draw the picture again. Um, so the car is attached to this. So what if instead of like cutting through the cable here and here, we do this? Okay, that's perfectly legal to do. The problem is when you go to the free body diagram, you get something like this. This is T. We have the weight. This is T. This is T, because those two are the same cable. But now we also have this force. That's a totally different thing, that force that the ceiling is applying to that pulley. And so we can't assume that that's T. And now we're sort of stuck. Our X equation doesn't do us any good. And our Y equation has two variables in it. So the reason, the bottom line is the reason I isolated the ones that I did is because that's the only place you can calculate.
So this is akin to taking a piece of the bottom of the
Right, right. Any other questions about this? And I can't remember actually if there are any of these pulley advantage problems on the practice problems or not. Has anyone looked at those? I guess I could look. I have it right here. There is? Okay. Okay. The way to do it is just to isolate the hanging pull, like any of the hanging pulleys, isolate those and the hanging mass. You always treat it the same way, and it'll let you calculate it. Okay. So that's the end of talking about how to calculate the force vectors applied to an object by a cable. There's one other type of force where we know the direction, and that is frictionless contact along a flat surface. Okay, so frictionless contact along a flat surface. And some examples where you would see this is if you have a box on the floor and the problem says frictionless, in this case, the box and the floor would be in contact with each other along the flat surface, which is the floor. Another example, if you see an object on wheels, those wheels are there to indicate that it's frictionless contact, unless it specifically says that there's friction in the wheels. And then another example would be if you have two objects pushing on each other like this. So in this case, the contact along a flat surface is this. In the second case, the contact along a flat surface is the contact between the wheels and the ground. And in the third case, you have it between the wheels and the ground, and you also have it there between the two bodies. And when you have this, when the chosen body is in contact along a flat surface, that contact force is A, perpendicular to the flat surface, okay, so now say that we're looking for a direction that's perpendicular to this flat surface. Point in the direction that's perpendicular. Okay, so half of you are saying up and half of you are saying down, and that's right. So we need one more bit of information. Otherwise, you know, it's not determined yet. And so that second bit of information is that it has to point toward the chosen body, away from the contacting body. All right, so here's an example. So if you have a cart that's on a flat floor, the free body diagram of the cart has a weight force, and then the only other force is contact along a flat surface. So the force acting on the cart is going to be perpendicular to the floor, and it's going to be toward the cart, away from the floor. So which direction is that? Up or down? Up. Yep, exactly. And in this case, people usually give that the variable name n for normal force. Normal means perpendicular, but you can call it whatever you want. The key is that you know the direction, and so you indicate that, you know, that variable that you use with it is a scalar, not a vector. Okay. And like, if you think about this case, it makes sense that that force has to be up, because gravity's trying to pull that cart down, right? If there isn't any other force counteracting it, the cart is going to be in free fall. It's just going to go right through the floor. And so the floor has to push up to counteract the downward force of gravity. Okay. But this is the way to think about contact along a flat surface. I do want you to notice one thing about this. This only holds for pushing contact. For pulling contact, treat the two objects as if they're connected by a small cable. Okay. So for example, if you had two carts, say one's being pulled to the left with 100 Newton force, and it's pulling this other cart along with it. Okay. Think of that as a 100 Newton force and just a little cable connecting these two carts. Okay. And then you just treat it using the stuff that we talked about with cables. Yep.
For the previous one for the free body
Mhm.
diagram, is there only one like end force that's on each wheel?
Oh yeah, that's a good question. Well, there really are two, and there really are four, probably. Right now we don't care about where those forces are applied, so we're just always going to lump it into a single force. But and the reason that we don't care is because we're treating everything as particles. So we're treating everything like it doesn't have any length dimension anyways. But when we start talking about rotations and stuff, it is going to matter. Like you can imagine, say that this normal force is 100 newtons, okay? If this wheel had 80 newtons on it and this wheel had 20 newtons on it, it would, you can imagine, so if this one was 80 newtons and this one was 20, it would have the effect of knocking this one up into the air and this thing would rotate, And so when we start talking about the tendency of things to change their orientation, it is going to matter. But for now, we can lump it all in as one.
Okay, so in the case of connected ones too, it doesn't matter that like the force isn't going to change based on weight. So if a smaller object's pulling a larger object, it's going to be one normal force for all four tires of them.
For all, right, it's going to be one normal force. That's right. Yep. Okay, let's do an example problem. Okay, so let's say that we have one cart here that's 10 kilograms, one here that's 15 kilograms, and it's being pulled to the right by a 50 Newton force. And let's say we want to calculate the acceleration vector and let's say that we also want to, second, let's say that we want to calculate the force vector on the 15 kilogram cart by the ground. And third, let's say we want to calculate the force on the 15 kilogram cart by the 10 kilogram cart. For the acceleration vector, we're going to isolate the whole thing. One thing we have to figure out is, are these two carts pulling on each other or pushing on each other? Well, if this 50 Newton force was acting over here, so we were pushing the 10 kilogram cart, it would push into the 15 to make them both move to the right. Okay, so that would be a pushing contact. But what we have here is, I mean, I guess you can always think of it mentally like, would this work if you replaced the contact with a small cable between them? Okay, that's sort of the intuitive test of whether it's pushing or pulling. If it would work, then they're pulling on each other. If it wouldn't work, then they're pushing. So in this case, would it work if you had a little cable between those? Would the 10 kilograms still follow the 15 kilogram? Yeah, so these are pulling on each other. Think now about, like, what if this 50 Newton force instead was applied over here, pushing that way, and you replace that contact with a cable? The cable would just coil up, right? It can't provide that. It doesn't have compressive strength. It can't provide pushing. So if the force is over here, you know that it's a pushing contact along a flat surface, and you're not going to replace it with a cable. Okay. Okay, so in this case, it's a pulling contact between the carts. Because you can replace the contact with a cable and you get the same behavior. So the free body diagram of both carts together. So there's the outline. The weight force is, the mass is 25 kilograms. So the weight force is 25 times 9.81, which is 245.25. And going around the boundary, we know that there's this 50 Newton force acting here. And where else is there contact from the outside world at the boundary of the chosen body? At the wheels, yep. And so I'm going to replace this, represent this as N, I guess I'll call it N total. This is the normal force of both of these two carts together. So Newton's second law says,
Can I ask a quick question?
Yeah.
The units on the 245 is
Everything on the free body diagram is Newtons.
Newtons,
Yep.
all Newtons. Okay.
Yep. Because you're only drawing forces on there.
Okay, and then the N total, and that's the N for normal forces?
Yeah, that's right. But that's including the normal forces, not just of the one cart, like the 4 wheels on one cart, but actually the 8 wheels of both carts. But we're lumping it all together again because we're treating this as a particle. Okay, so Newton's second law says 0, negative 245 plus 0n total plus 50, 0 is equal to the mass, 25, And then do we know anything about the acceleration? There is one thing that we assume we know in problems like this. We assume that the carts are going to move along the surface. They're not going to jump up off the ground, and they're not going to sink into the ground. Okay. So we're going to assume that the acceleration takes place totally in the x direction. Okay. So I'm going to write, it's an unknown acceleration, but I'm going to write it a0. So the first equation here says 50 is equal to 25a. And that says a is equal to 2 meters per second squared. So how do we go from this value to the acceleration vector? What's the acceleration vector? Yep, that's right. So you can just think of, in Newton's second law, this vector here is the acceleration vector, okay? This vector here is that force external, that's the one that's given. This vector is the force on the carts. I guess that's the force on the wheels by the ground. And then this is the force on the carts by gravity. And so as you calculate these variables, you can just plug the values back in here to get these individual forces and this acceleration. Okay, so the acceleration vector is, plug the 2 meters per second squared into the acceleration vector here. You get 2 meters per second squared, 0. Any questions about that?
Is that, force vector CG, is that supposed to be DC or is it supposed to
That's the force on the carts by the ground.
be on the carts by the ground?
Yep. Okay, so now we want to calculate the force the ground applies to the 15 kilogram cart, the force on the 15 by the ground. So I'm going to isolate, draw a free body diagram of the 15 kilogram cart. What forces are acting on this cart? Yep. So 147.15. And now think about going around the boundary. Where are outside objects touching the chosen body? Yep, this cable that we made up. Call that T. There's still that external, that 50 Newton force is still applied to the 15 kilogram cart. And one more place. The wheels, yep. So I'll call that N15. And now Newton's second law says negative t0 plus 50 0 plus 0 n15 plus 0 negative 147.15 is equal to the mass, that's 15, times the acceleration of that object. Do we know what the acceleration of the 15 kilogram cart is? Yeah, they're all locked together. They're all moving together. So we're going to use our answer from before. So this is going to be 2, 0. Out of these 4 force vectors, which one is the force vector applied to the cart by the ground? What we're trying to solve. Yep. So this vector here is the force on the cart, or let's say the force on 15 by the ground. So if we can figure out what this N15 is, then we can solve this. The first equation says negative t plus 50 is equal to 30. Okay, so the tension here in this cable is 20 newtons. I didn't ask for that, but we can get that from the first equation. And then the second equation says N15 minus 147.15 is equal to 0. So N15 is equal to 147.15. And so now that we have this value, we can plug it back into the vector, and we get that the force on the 15 by the ground is equal to 0, 147.15. Okay, so I didn't ask for the force on the 15 by the cable, but that would be this, the force vector on the 15 by the cable. Okay. And so if we plug this tension in there, we can figure out what that is. So let's just calculate that and set that aside, because something really trippy is about to go down. So the force on the 15 by the cable is equal to, so the tension is 20 newtons. So it's going to be negative 20, 0. Okay. And you can think about that as that's equivalent. There isn't really a cable there, right? So you can also think about that as the force on the 15 by the 10. Okay. And now let's calculate the last thing that we're supposed to calculate. What's the force vector applied to the 10 by the cable, which you could also think of as the force on the 10 by the 15. Okay. So to do that, I'm going to isolate the 10 kilogram cart. What forces are acting on this? Yep. You should always say gravity, because then you know I'm not going to ask you anymore, like you've already done. That's just like standard, like taking classes 101. You don't want to get asked the hard questions. So you say the easy one as fast as you can, you know. So the weight is 98.1. And then go around the boundary. Where are other things contacting? Well, over here at the cable, that cable force, you know, that cable tension is the same as the cable tension on the other side. We calculated, what was that, 20? So we know that this is 20. And then the other place is the normal force applied by the ground, you know, applied to the 10 kilogram by the ground. And so Newton's second law says 20, 0 plus 0 and 10 plus 0, negative 98.1 is equal to the mass, 10, times the acceleration, yeah, 2, 0. Yeah. Okay, so I guess the way I set it up here, you just see 20 is equal to 20. That shouldn't be too surprising. But it does show that, you know, we were thinking about things right with this cable force. Everything worked out. And the second equation says the normal force on the 10 kilogram cart is equal to 98.1. Okay, but this thing here, this 20, 0, that's the force vector on the 10 by the cable, right? So the force vector on the 10 by the cable is equal to 20, 0. And since there's not really a cable there, that's the force vector on the 10 by the 15. Okay, so I just want to point out the relationship between the force on the 10 by the 15 and the force on the 15 by the 10 that we just calculated in the last step. They have the same magnitude and opposite directions. Okay, so the force on the 15 by the 10 is equal to the negative force on the 10 by the 15. Weird coincidence? Join us next class for the exciting conclusion. Well, that's not a weird coincidence. That's actually, it's called Newton's third law. It's probably the second most important equation in this class. And using the subscript notation, you can define Newton's third law this way. The force on body A by body B is equal to negative force on body B by body A. Newton's third law is the law you've probably, you know, heard something like this before. It's worded something like, for every action, there's an equal and opposite reaction. but thinking about it this way can get you into trouble because there's nothing to make you be real specific about what the chosen body is, what the contacting body is. The way to think about it is any force, define it as a force vector with that subscript notation. And Newton's third law says something about the opposite set of subscripts. So if the force on body 15 by the ground is equal to 147, say, that's what we got in the last example, then the force on the ground by the 15 kilogram cart is positive 147. Okay, it's equal and opposite. And I think next time I'll spend a little time talking about this. But this is, Newton's third law seems weird to a lot of people. Like, it sort of goes against your intuition in a lot of ways. Like, for example, if you think about a 200-pound, baseball player hitting a baseball, comes in at 100 miles an hour, swings the bat, it takes off at 120 miles per hour. It's sort of hard to believe that baseball is applying the same amount of force to the bat that the bat is applying to the baseball, right? I mean, that seems odd because you never see the baseball player go flying, 400 feet. So I think I'll talk about like how that actually does work, why that actually does make sense. But that truly is what the law says. Like, if Newton's third law says the baseball applies the same force to the bat that the bat applies to the ball. So if you have a minute to think about it, see if you can sort of straighten that out, make sense out of that in your own head. And we'll talk about it. You can ask questions about it in class on Monday. Okay, that's it. Have a good weekend.